Yo. So, today I'm going to be trying to get anything to come out of this encoder. I need to solder some headers onto this thing. It takes SPI communication protocol, so I'm going to have to figure out which microcontroller or board I'm going to use to communicate to this thing to get any sort of data out of it. For context, I want to somehow fix this sensor onto that motor over there. And in principle, how this works is there is a magnet here that gets fixed very close to this at an offset, and as the magnet turns, the encoder will measure that angular displacement. So in reality, I need to fix this magnet to the motor somewhere, and then fix this somewhere in close proximity to it. And then one needs to rotate, and then the other one stays fixed. I've never used this before, so I'm gonna have to figure out how to interface with it. And so my initial thought was I would pass it, well, I think in the final phases of this, switch screens here. You see you can kind of see in the bottom left corner, this O drive here, there's some jumpers here, and these can take signals from encoders. So eventually they're going to wind up being processed by this O drive motor controller that drives these hoverboard motors. But before I take that large leap, passing this into essentially a black box, I don't know exactly what the firmware on here is doing. I can interface with it, but I'm not the one who wrote this code. And I want to kind of get a little bit more acquainted with what this sensor is doing and how fast I can get data out of this sensor. I mean, that's kind of pre-established by the SPI communication protocol, but I just want to mess around with it. So the goal of this stream is to just get anything out of this small little sensor here and put a magnet close to it and get something. So hopefully we can do that today. So back to how I'm going to do that. A couple thoughts went through my head. I can use an Arduino and use a SPI communication library to do this. Or I can use the Zybo board, which is in this server rack up here, the middle shelf. So I think what I'm going to do is, since I've already messed with that last stream and I know that that's working, I'm going to see if I can get SPI communication to work out of the Zybo board. I've done this sort of before, but never with an actual sensor device. I think I might have done loopback, and it might have not been on that OS. It might have been on another OS that I created. So this should be interesting, especially if it doesn't have SPI. There's a couple steps that I would have to do. I would have to make sure that it's sort of a beast to get working. That's why I'm sort of hesitant in doing this on the Hoverboard. But I don't know, I guess we'll cross that bridge when we get to it. But basically there's a mux inside of the Hoverboard that can route SPI either through programmable logic or the FPGA. In case for those that don't know, the Hoverboard has an ARM processor and an FPGA in the same silicon die. And there's an interface, like a programming interface that you can use. It's called like Vivado, where you can program certain communication protocols to go through the FPGA fabric and out through pins, or you can choose to have it be routed through other means, like to go out through pins just from the processor and not being routed through fabric. Either way would work. It's just whatever your application needs. Oh, nice. You're using Vivado? Yeah. It can be a steep learning curve, but we'll see if I have to start messing around with that today. Okay, let's share my screen. I think the first thing that I'm gonna do, so there's actually something of a, oops, let's see. There's sort of like a cheap way to access SPI, just as like a command line utility. It's called SPIDev, and we'll be taking advantage of that on the Linux operating system. Okay, I'm gonna share my screen. Zoom in. I need to turn on Hoverboard. So let's do that first. Okay, this is this far one, right? There's that one. Okay. Hoverboard should be on. And last I checked, we have SSH working. Well, it was that one, so let's go back to here. It's the IP. So we should be able to just SSH into this, hopefully, if it's up. Yep, cool. Okay, so the first thing that I want to check is if we have SPIDev. So I'm just going to do SPI, tab a couple times. Yeah, cool. So there's some SPIDev stuff. I believe SPIDev test is the command line utility. Okay, and then let's check like dev devices. Yeah, okay, sweet. All right, so what this means is that this is kind of cheating a little bit, because like I pre-made this operating system and I had to like make this with very specific configurations. Like this wasn't the default mechanism. Like you can put these SPI tools on there pretty easily. If you're not making a custom operating system, I think the package name is SPIDev or something. I don't know, you can Google it, but it's really easy to get these utilities on there. What's more difficult is getting the device recognized within /dev. For those that don't know, /dev, these files are very special type of files. Like they're either char or character device files. There could be like block device files. In fact, you can see this if I do -L, go to dev. If you've ever wondered what the C is in the front, right? Normally you're used to seeing D probably for a directory. C is a very special type of file, and that's a character device file. There's a couple other ones. I'm not familiar with all of them. I think B is like a block device. But basically what this means is that these are like Linux drivers or static drivers that are deep within the Linux kernel that are exposing a specific interface for you. And these interfaces allow you to interact with hardware. And that's why you see things like FPGA here. You can do stuff with the FPGA. If you've ever seen like MMC, this is memory management controller, block 0, partition 1. So it looks like there's like some SD card or something along those lines, and then there's 2 partitions, P1, P2, right? This is basically your access to the outside world through dev. So at work, what I would do is I would typically, if I want to access anything from the outside world that's not already done for me, I would typically make a Linux driver, and I would continuously, iteratively plug it into the Linux kernel. If you want to see kernel modules that are just loaded in by default, that's lsmod. That's funny. Unrelated, this is a driver that I was working on a while ago. It converts AXI to SPI. It says SPI here, but this is actually completely unrelated to some of the stuff that I'm doing with SPI dev here. SPI has 2 different modes that you can work in. There's a controller mode where the Zybo board would be the initiator, or the processor would be the initiator, so sending out packets. And then there's a peripheral mode where it's you're accepting those packets. Accepting packets is difficult from an operating system perspective, because if you think about what an operating system is, it's all about obfuscation. It's trying to make things easier for a user to interact with this huge monolithic system. And to do this properly, you have to obscure a lot of stuff. Otherwise, you'd just be writing bare metal application code, which is kind of tough. But you want that obfuscation. But as a result of having obfuscation, that usually leads to lack. That leads to lack of awareness of what the lower level stuff is doing, and you're not able to control timing as well as you could. So for example, the Linux operating system might be off doing some other process because some other tasks are running on some other cores, and then it's going to hop to another core to do another task, another core to do another task. The problem, that's great in general, but the problem when you're working with hardware devices is if there's really tight timing requirements, you might not be able to make those timing requirements. And that's the issue with SPI, where if you are a peripheral, you can't meet those timing requirements. So what you have to actually do is, in the example of Zybo, you can implement something in the FPGA to act as a peripheral. And so that's what I actually did here with this driver. But today, we need to act as a controller to interface with this chip, because this is a peripheral. So you can go both ways depending on what you're trying to do. Okay, so we have SPI dev here. What I need to figure out is what pins SPI dev 0 is on. I might be able to figure that out by looking at the device tree source. The problem is I need to remember what device tree source I was using. Probably haven't touched this in a while, so I would imagine it's probably under workspace. Let's open up Vim. Let's go down the rabbit hole here. So this would have been a Yocto build. So this Yocto builds allow me to make custom operating systems. We went over that in our first stream. Where would I okay, it would have been in RoboDog. This is a layer that I created. Potentially in recipes kernel. ESP maybe? Oh, I think I put in U-boot. U-boot is a bootloader that needs a device tree source. Yeah, this is the driver that I was working with. So I'm pretty sure I probably have this DTS registered for this operating system. Okay, here's SPI. So these are SPI nodes in the device tree source. And this is probably where the two, so if you remember, we had two registered in this, I'll just view it here. We had two registered, SPI dev 0.0 and 1.0. This is like equivalent to like having a chip select, like two chip selects basically. But it's interesting because one is disabled. So I'm not sure where the 0.1 is coming. Oh, there's one up here. That's what it is. Okay. So here's SPI. This is SPI dev. This gets picked up by the SPI dev driver. Here's another SPI node, and then there's another SPI dev here. It looks like they both work off of different clock frequencies. So you can specify clock frequencies in here. Okay, what I'm interested in is the pin. What pin is this out of? I don't immediately see that here. Maybe I'll Google it. Which pin? Let's see what else is up here. Okay, if I'm using SPI through the PS region, which is the processing system, so the MIO pins, this is just basically pins out of the processor and not routed through the programmable logic like I was talking about earlier. Then it looks like it's 10, 11, 12, and 13. By the way, this is what I'm pulling from. I just asked ChatGPT. Those are PMOD pins. Let's see if I can get a diagram. There should be like a pinout. Zybo pinout. Zybo C7 reference manual. That should have it. Okay, let's see. Oh. Okay, we have the C7-20. It's SPI flash, which is different. Oh, MIO pins. What MIO pins did it say? 10, 11, 12, 13. 10, 11, 12, 13. And 1, 2, 3, and 4. JF. And that's assuming I didn't map them to something else in the FPGA, because there is a bit stream running on this thing, an FPGA bit stream, but I don't think I wouldn't have changed anything with SPY here. Where's the F? Oh, it's right here. Okay. Also, I could probably just search miso. That would probably mostly. Oh, interesting. I could just open Vivado and see what those naturally get routed to. Because it's interesting that I'm not finding Mosi or miso in this list. So I'm just going to create a new project. Let's do a temp project. Yeah, don't need to worry about any of this stuff. The boards that we're using, Zybo 7-20. Create block diagram. Hey, Julie Ermay. Hope I pronounced that right. How you doing? Yes. No, where's the PS block? Zinc. Okay. So here's SPY. So if I were to select SPY and have Neo pins, so it looks like the default is 16 to 21, 28 to 33, 40 to 45. What about SPY 1? Ah, SPY 1 is 10 to 15 like it was saying, right? Where is it? Yeah, 10 to 13. There's two SPY controllers, SPY 0 and SPY 1. So, and 10 to 13, Mio 10 to 13. So I like, this is for the Zinc chip, which means I have to play by the rules of this Zybo board. So I need these specific Mio pins. Otherwise, who knows where the pins are going to be routed to on the board. But I know these pins are routed to PMOD JF. PMOD's just the connector. I'm just thinking this is going to be a process, because that means I'm going to have to do most likely new bit stream, unless I'm already using SPY. But I can't remember the FPGA bit stream that's on the FPGA. It would probably be ideal to just make a new one, just so I know what's on it. Neo pins are being used by SPY. Like if I configured it in the previous bit stream, but I probably didn't. me see if I had my previous Bravado projects in here. It would probably be in dev. It would have probably been this one. These are the tickle scripts that I made for it. So you can actually, you don't have to run Vivado manually, like through a GUI. You can actually run tickle scripts and that automates the process. I forgot I made this. But the problem, oh no, I was gonna say the problem with this, I need Vivado to be running in Linux, but no I don't. I can actually run this. I can run this on my Windows computer where Vivado is. So, oh, build all probably runs both of these. Yeah. Okay, I think what I'm gonna do, I'm pretty sure this is the project that's on the board. So what I'm gonna do is I'm gonna run this. I should actually be able to, like, can I close this? I should be able to do this from here. Close. Don't save. And I should be able to execute, yeah, run tickle script. And I should be able to go to where the tickle script is. But it's not in my C drive. Would this be in? Let's see. Would be dev. Okay. I'm using WSL, which is Windows Subsystem for Linux. I should. Maybe. I don't know if it uses network drives like this. This is how you access it in File Explorer. Let's see if it will understand what that path is. All right, I'll copy this just in case. All right. Yeah, this. Do you understand this? Huh, well, it looks like it did. Apparently invalid in design selections. Sure. I mainly just want this to build out. I don't know if I don't know if it builds. We can try it again. Tools, run tickle script. Let's do build all. try one more time. Let's close this. File, project, tools, run tickle script, build all. Oh, couldn't read file. Oh, maybe it couldn't reference it. Where does it think I'm at? Oh, okay. All right, I might have to make here, I might need to do something real quick in File Explorer to get this to be recognized. Let's try this. Oh, maybe that wasn't right. All I did was create a network drive, but I think I needed to create like a C drive. Map network drive, I think that's what I need. Yeah. So I'll do it like on Y or something. And I'll specify this location. Access. Is it because I'm already using it here? Let's try this again. Map network drive. A Y drive, for example. Nope. Why is it not connecting? I might just end up building it. All right. Oh. It looks like I was like referencing it this before, like I mapped it to a Y drive, it looks like. The bummer is not wanting to cooperate now. I could try mapping it to that same exact location, but yeah, that's a good idea. I think what I'm trying to do right now is just try to get any information out of the AMS encoder right now. So you're one step ahead of me. let's just create a new project. I'll go through this, and this should be somewhat interesting, hopefully, to see how to create a Bravado project for the Hoverboard. I'll just do a temporary one right now. I don't want to add any sources. I do want to add a constraints file though. All right, create a block design. Add the zinc block. Okay, so we want, oops. I think, well, we'll see. I really only need one. I guess it matters which one for the Mio pins. And pmod f. Let's go through 1 through, or no, sorry, 13, 10, 11, 12. 10, 11, 12, 13. So pin 1 through 4. 10, 11, 12, 13. So that's not SPI 0, that would be SPI 1. 10, 11, 12, 13. So SS is slave select. This is going to be MOSI, MISO, clock pin, slave selector, chip select, is MIO 13. Yeah, so let's go with that. So what I'm doing here is there's a mux within the Hoverboard. I'm just specifying that the chips, the SPI controller signals are going to be routed through the PS region straight to these pins, as opposed to, like, for example, through the fabric. And I'm routing specifically to these pins. I can route to other pins if I want, but these pins are probably not connected to anything on the board, on the Hoverboard. And all I really care about is SPI right now, because I'm just using the Hoverboard as a way to just talk to the encoder. So let's go with this. So SPI 1 is checked. I don't think I need anything else here. Hopefully. Yeah, let's go with this. So you can run block automation. This will set up other blocks for, like, you know, the zinc processor is also going to be connected to DDR. So it's going to add those blocks, or ports, I guess, in this case. I'm not connecting anything for this AXI port. This AXI port, I know I'm giving like high level. This isn't necessarily like specific to encoder stuff, but you know, I'm not using an AXI port. I think if I actually run this, it's going to give me an error because I'm not using AXI. So we can go in and say I'm not using it, which I think is here. Yeah, so uncheck that. That port will go away. And then I can run validation, which is the check mark up there. And that's really it. At least I think it is. It's been a while. Let's save it. Generate a bit stream. So this is going to generate basically a program that we flash onto the FPGA. No, like this is separate from the processor, right? Vivado is an environment for interfacing and programming the FPGA. It also does something else that it doesn't really advertise, which when this gets done building and synthesizing and doing place and routes, what's going to happen is I'm going to export something called an XSA, which is a Xilinx shell archive. And that's going to have header files for a first stage bootloader that will configure the mux to tell it what SPI ports it should be using. What error is this? Let's see. Top module. Yeah. Okay. So I should have. Okay, so I need to do more than just create a block diagram here. I actually, creating a block diagram is just that. It's just a block diagram, right? It needs RTL, which is real-time logic, or HDL, hardware descriptive language, to actually build. This is the programming language of FPGAs. And so I need to create an HDL wrapper, hardware descriptive language wrapper. We'll let Vivado manage updates. I don't really care about this bit stream right now. So you can see that it just created this .v file, which is Verilog, and now the block design is underneath this. So if I double click on this, you can see the code that was generated from this block diagram. It's not super complicated. These are like all the pins and connections that it's making. This is the block of design 1, which is this block here. And then you can start going deeper nested into this and like, what other stuff is, what other RTL or HDL is inside of this block and stuff. But don't need to go down that rabbit hole for this. So now we should be able to generate the bit stream. So it's running in the oh, you can't see that because my face is in the way. You see that it's running up here. I'll bring myself down here. Takes a little bit to synthesize, so it's going through synthesis right now, which it basically looks at your current configuration of all these logic gates and it tries to make a better solution. I mean, this is like a relatively simple design here, but you can make something way, way more complex. So the synthesization step is basically trying to make sense of all the logic gates and then try to simplify it. I'm sure it does a lot more stuff than that, but that's one of the steps. And then after synthesis, it'll run place and route. So that's where it's like actually routing all the connections throughout the FPGA. So while this is running, it's going to give me a .xsa file, and I sort of have everything running through Yocto. So I'm going to have to remember what I was doing in Yocto here and where I'm placing stuff. So this is my layer. That I created for RoboDog. It's probably in layer.conf, right? So I'm using 2023.2. That's the Vivado version I'm using. Yeah, and this is the XSA file that I'm using. SPI reference design. Okay, located. I'm glad I put these notes because I knew I was not going to remember this if I went back to this. Okay, so it's located in Meta, RoboDog, Recipes, BSP, HDF. Okay. Yeah, okay, so this was like a default XSA, and keep in mind an XSA file is what I'm basically building right now in Vivado. It's getting there. It should end pretty quickly because this is a really small design. So now it's doing place, then it's going to do route. So what I'm going to have to do is I'm going to replace this XSA, and I'll probably name it like temp or something. Or I'll keep this here actually. We'll just comment it out, make a new one. Temp spy. We're just enabling spy. I guess it's spy 1, spy channel 1 that we enabled. Cool, it's done. I don't have to show this, but let's show it anyways because it's sort of interesting. So when Vivado runs, you can open up like an implemented design, and it's going to show you physically on the chip where your design is running. And so if I zoom in close enough, you can see like different logic gates, which is pretty cool. Yeah, this is all the FPGA, and these are like I/O basically, like routing out to pads on the chip. Yeah, so I thought this was super cool when I first saw it. I think this might be, no, it's not, it's just a different color. So like once you develop a large design, you'll start seeing like export hardware. Include bitstream. And then what did we name it? It was like temp spy 1. Sure, we can do it under temp. Cool, I think it's done. So here it is. This is temp spy 1. I'm going to relocate this. Projects. RoboDog, workspace, dev, no, not dev, hockey, build, temp, no, not temp, it's meta RoboDog, recipes, BSP, HDF, files, that's where it was, let's paste it there, okay. So this is where the other XSA was. It's temps by 1 XSA. So we're going to be using that as we're building up Yocto. I haven't built this in a while. So I need to remember how to get into the Docker container. I'm changing everything here that I think I should be changing. So let's go out one. I'm going to do Vim at this level because I wanted to see the build container, which is right here. Or sorry, the Docker file. That's how I run it. So I also have it on GitHub too. GitHub. We just do RoboDog. I also have a README. So this is what I do for building. Although I probably already have a Docker image for this, right? No, that's probably another one I was doing. Okay, let's do another one for this. It's called RoboDog. I was curious about your other videos. Are you using FPGA in this RoboDog project for some technical reason or some personal reason, like to practice the technology or because you like it? Both. So I do like FPGAs and I want to get more familiar with them. But also there's definitely a technical reason as well. You have a lot of flexibility when it comes to what you do in an FPGA. And the thing is, I didn't know exactly what direction I wanted to take this RoboDog project, and FPGAs really are a good path to take if you want flexibility in your design. Because, I mean, you control the programmable logic. It's almost as flexible as you can get. So that is something that I definitely wanted. As I got further along with the RoboDog project, I feel like what I want out of this project is probably not, it can't be fully contained within the Zybo board. Like lately I've been interested in like machine learning, specifically like machine learning hardware. Like if you take cutting edge processors or system on chips nowadays, like look at AMD's recent processors. Like some of them are like the AMD Versal, for example, or Microchip is also creating like very bleeding edge processors as well. And all these chips, like most modern chips, will have an FPGA in the silicon die. They'll have a processor in the silicon die, and then they'll have some other acceleration hardware in the silicon die, like DSP engines or AI engines that will help accelerate different workflows that you're doing. You know, Zybo's pretty, I think it's kind of old at this point. It's nice that it has an FPGA in it as well, and it can kind of be an entryway for you if you want to get like exposed to FPGAs within the same silicon die as the processor, because there is a certain like development method that you have to do to really leverage both domains. Like, I mean, you have to use Vivado, you have to understand the interplay between what you get out of Vivado and how that feeds into your software side, right? There's a PL region and then there's a PS region, PS being processing system side and the PL being programmable logic side. And just knowing how to interplay between both of these really sets you up to take on the higher, more modern processors today, which are even more complicated. And you can just do more interesting stuff with it. Like, it would be pretty cool if you could do a lot of different sensor processing on these embedded systems, which, I mean, they're typically supposed to be lighter weight, lower power, smaller size, basically swap size, weight, and power. You want all those things to be low. And so these processors that are coming out, they're able to pack more into a single chip. Because I've worked with a lot of designs that were, you have a separate CPU and you have a separate microcontroller, and the CPU talks to the microcontroller, and then you have to establish a communication protocol between them. You have to establish a CRC and software layer on top, so that you make sure that data packets are getting to the desired destination properly without you dropping packets, or if you do drop packets, how is your recovery mechanism, right? You don't have to worry about any of that when it comes to like inter-chip communication, because it's on the silicon die. Like, there's less chances of, like, someone spent the time at whoever made this ASIC, whoever made this chip, basically, to make sure that those connections are solid and that they will work. So it makes sense to go to these sort of like upgraded platforms, like that are trying to do more on a single silicon die. So to me, the Zybo board was just an entryway to that. I always kind of wanted to maybe migrate away from the Zybo board and go into maybe like an NP-SoC or like MicroZ. I mean, maybe MicroZ is still Z7020, which is the same as the Zybo board. Whatever board is the NP-SoC. I'm sure that they have some dev kits for NP-SoC, AMD. I mean, ideally, what I actually want to try to do is I would like to try to create my own board. I have a lot more experience in software and developing operating systems and Linux drivers and stuff. Hence me like covering that a lot on this channel, just because I'm super familiar with it. FPGAs, like, I dabble. I do some of that stuff at work too. I wouldn't say I'm super comfortable with it, so that's why I want to also introduce it to this project too. I'm really not familiar at all with like doing board design. I've done it once at work, and I've been exposed to it a lot, but I want to do more board design. Another interesting thing too is, like, I've seen people do really interesting things with motor control on FPGAs, especially with brushless DC motor control. And so I kind of wanted to try my hand at that too. Like, you have very fine control over the signals that you're outputting out of an FPGA. I mean, I guess you kind of, maybe that's not an argument, because you kind of have fine control over like microcontrollers too, but I don't know. I feel like FPGAs are a little bit more flexible. It's running step 2 out of 7 right now. Step 1, so it's running this one. Should almost be done. See, after this, do a docker run command, chown source build.sh. Yeah, this might, actually no, it shouldn't take super long because the workspace is already here. Because if you've ever built Yocto before, like it can take like an hour or longer, depending on what you're trying to build. But I'm pretty sure I have all that stuff built here. And once you build it once, everything's cached in here. If I were to run a spy dev test, just seeing what the command would be. Spy dev 1.0. Probably specify the speed. 50 megahertz. Spy mode is max. Right, and then the input. Like specify results stopped in. Oh, cool, it created it. So what's the result stopped in? All zeros. Makes sense. Right now I'm just seeing if I just by chance I have like the spy connected. This doesn't say that I do or not. I have these dev drivers, dev devices exposed, but that doesn't mean that these are routed to the correct pins, which is what I was concerned about, which is why I'm building this in the first place. done. I was just seeing how to create like a ramp file real quick. Yeah, okay, so this is like example input data. I can check, like, I can probably do like a loopback or something just to check that I have SPI working properly in the Zyvo. But I would use probably something like SPI dev, the input is, right, I was input, yeah. Ramp.bin, output would be results.bin, and then xxd, which is just like hex output on a binary file. So if I had like input looped to output, so like looking at this, oh, I guess we would have to look at the Vivado to see what pins I would route. Let's go to the wrapper, open block design, SPI1. So Mio 10 to 15. So I like, before I try to build Yocto real quick, let me just see if I can loop back Mosi and Miso. That's Mio 10 and 11. And Mio 10 and 11 is pin 2 and 3. 2 and 3 on JF. 2 and 3. 2 and 3. JF is there, power is there, ground is there. Power and ground. Right? I'm looking at this right. Power, top left. Ground. Right? Ground was the second one. Yeah. Okay, so pin 1 and 2, we go this way. Top right, and the one right next to it. All right, I'm gonna try to connect. I'll bring you guys over with me. Let's see. Don't really need that webcam, but let's see. And 2, 3 on JF. J is over there. Okay. See it? Let's get just a jumper here. Kind of sketchy. Everything's bolted in though. I'm gonna ground myself. in pin 1. Okay. All right, now it's in pin 2. Nope. All right. I would have expected that to be the ramp file, but didn't get anything. Just to make sure this is not like on 0, right? Interesting. Got something, but it's not what I expect. I didn't pass in anything. Whoa, that's interesting. Is 50,000 too fast? Well, first of all, this tells me like that can't be a coincidence. Like that's the ramp file that I passed in, which means it is connected. Let's try a different speed. This is 50 megahertz right now. Let's try 20. Nope. Let's try 25. Nope. 30. No. 5. Oh, I'm just reading, duh. Need to actually output something on the line, right? So that's what the input file is. Let's try 20. No, nothing. Let's go back to 50. So let me look at the RAM file again. So it starts at 0. And if I go really slow, like at 5, oh, that worked. That's 5 megahertz. Is that consistent? Wow. I think it was connected this entire time. I'm curious, if I were to make a new design, like does it just connect that SPI line? Because when I clicked on this again, I noticed that there's a lot of connections pre-made. Like I didn't make these connections, right? And I think that happened when I ran the block tool. But I'm kind of curious, if I close this design, can I like make a new one? There's new. temp. Sure, we can add constraints. It's fine. Board with Zybo. I just want to see if I run block automation, if it will enable a specific SPI. Okay, yeah. So I'm not going to touch anything in this. So nothing's checkmarked. So if I run block automation, right? Just connecting DDR basically to fixed IO. And then if I were to go back into here, okay, these are selected, but SPI is not. Okay, so in my design, I probably did something that connected SPI. I would have had to have, like, otherwise these aren't connected. Okay. Well, regardless, that's great. So now I just need to connect to this thing. So I know that I'm using 5 megahertz. 5 megahertz seems to be consistent. In fact, we can do something like XD results. Maybe it's not consistent. Am I running 5? Yeah, 5 kilohertz. Oh, maybe I'm like, no, I shouldn't be like reading it too quickly, right? All right, I'm gonna reboot this. It's weird that it's giving me mixed results. Usually I see that when the clock speeds are messed up. And typically, like, you'll have like a default clock speed set on the device tree source. Although, I mean, it seems like it's configurable through that Linux utility. Probably using this. Saying 25 megahertz. And it's interesting that I'm doing this off of SPI 0. It's supposed to be SPI 1. Weird. 250. If I do 1 megahertz. I don't get the discrepancy. What if I go back and forth between 2 different ramps? This is what I was using. Specify this? Yeah. Oh, but I overwrote ramp. I want ramp to be at 32. Let's have ramp 2. 32 to 64. So ramp and ramp 2. Oh, that's ramp. Alright, and this is ramp. Well, let's look at ramp 2 first. 20, 21, 22. This is in hex. All the way to 3F. Yep. Weird. It's like there's data still buffered up in this. Well, this is interesting. There's a loopback mode. Yeah, what happens if I do loopback mode? Right. So, 0. Why? Does it need a speed? Set spy mode. All right, we'll see what it says for doing a loopback test with spy. Basic command. Interesting. Oh, that's cool. I didn't know you could do this. So you can send an ASCII with it, with a -P. Is that on here? Don't see it. -V though. Let's verbose. Show TX buffer. Yes, that would be useful. Let me do that with what I was doing here. So if I do ramp, and I'll show TX. Oh, okay, so that means I don't need XXD results, or I don't even need to print it out. Yeah, that's what I'm sending. That's what I'm receiving. Wondering if It's like I need to flush things out or something. Why was it working a second ago? It just stopped working. Just different values, huh? You ramp 2. Ramp 2 again. Yeah, they're like all okay. Now it's new values. I'm gonna try. Okay. Try rebooting, then I'm going to try 25 kilohertz. I think that's what it should be in the device tree source. This should be SPI 0 and that should be SPI 1. Seems like it's like lagged by 1. So that's 20, starting on 20. Starting on 0. Starting on 0. Then I'll move back to this. Okay, what if I just started on 5 megahertz? Alright, while this is going, this looks like it finished. So let's do Docker run. Yocto build. Temp SPI. This is running from, what did I call it? RoboDog image. Docker run. RoboDog image. Okay. this one in. Is there workspace? Yeah. Actually, no, there's not workspace. Should be home go to. Let me just run Docker run from here. RoboDog image. Okay, there we go. What embedded systems do you plan to use to run machine learning algorithms on the RoboDog, Raspberry Pi, NVIDIA Jetson? I would love to run something like the Versal, but that's probably too expensive. So I would probably just upgrade to a NP-SOC and then use IP cores for machine learning specifically. So I'll just drop in IP cores into like a Vivado project. There's a lot of good open source like machine learning type IP cores that you can get now. Why isn't this cooperating? Okay, well this is doing its thing. Go back into this. How about you? Do you use any like machine learning platforms or anything along those lines? It seems to like something weird is happening with the buffer. If I like increase it, it doesn't seem to help all that much. I don't even know if this is really doing much of anything. Going to the next spy channel definitely doesn't do anything, right? Yeah. Interesting. I think I know why this is taking so long. It's because in Workspace there's a lot of files in here. Yeah, that's why it's taking so long. It's a bummer. We were so close to getting this working on this side that I didn't have to like replace it. I'm surprised, honestly, that SPI channel 0 is even on. So I connected pin 1 and pin 2. I shouldn't have to connect anything else. Yeah, I should only have to connect MOSI and MISO. I mean, the fact that I'm getting like a lagging indicator means that there should be something on the line. Right, so now I'm getting like within this range of the ramp 2 file. And then if I go back to ramp 0, I'm going super slow speed. So 100 kilohertz, 1 megahertz, 10 megahertz. So it's still in the high range, but you can see that it goes to low here. It starts on 4. Why does it start on 4? So weird. Might be able to like, oh, there was a command. ChatGPT would probably know. There's a command to like print out the entire device tree source of your current running operating system. I know that I said I was looking at it here, but just to doubly confirm that this is what I'm actually looking at here. There should be a way to view a device tree source on the operating system that you're on. So the way, there should be a command. I'm gonna ask ChatGPT how to display command to display DTS in an embedded Linux OS. I think he used, I think I remember your device tree compiler. You want to dump the whole device tree? I thought there was like a DTC command that wasn't just dumping into a file, but this might work. Let's see what this does. Not what I was hoping. I could probably walk the file system though. So this is like representative of what the device tree. Do I have a DTC in my? No, I don't. So this is like representative of what you'd see in a device tree source. So the parent node, what was I in, Axie? Yeah, in Axie. So Axie, SPI, SPI-dev, Test the Yellow 8 model in different optimized formats. Oh, nice. Engine format because it showed better results with Jetson Nano. Oh, well. Nice. Yeah, I haven't actually worked with Yellow myself. Heard a lot of good things about it though. That's cool. Yeah, I dabbled a lot in NVIDIA, specifically like really old NVIDIA devices, like an NVIDIA TK1. It was a long time ago. They stopped doing system on chips, and they went on to system on modules. So you can't buy system on chips anymore. They stopped on the TK1, which was unfortunate because the company that I worked for like a long time ago, they had you would just buy chips from NVIDIA, and then you place it on a board, and then you'd make your own like circuitry around it. Now you have to buy the SOM with it. In some cases that's good, but in some cases it's bad because you can't select what's in the SOM. Trying to think if there's anything we can do from this point, other sort of testing while this is still running in the background. This didn't show me what I wanted to show me, basically. I have no idea what that is, unless it's like binary. It shouldn't be binary. Let's see. Anything else we can do? Might play with this a little bit more. What other options are there for SpyDev test? Oh, there was a -P. It's like I need to flush out part of the buffer. I need it to be an exact length. Is there a certain length to have when using Spy? Seems like and I'd test piracy. See what that says. Full duplex, I saw that, right? No, that's dual transfer. It sends blocks of data, default 32 bytes unless you specify otherwise. Expect synchronous transmit receive, but Spy's full duplex, so every clock cycle both TX and RX are active. If you loop back wiring, your Spy setup isn't perfect. You can see a lag. The RX data looks like the TX data, but shifted by 1 or more bytes. Interesting. Typically, the reason for RX data lagging behind Spy flex is every byte you transmit, a byte is received at the same time. If you start sending before wiring is stable, during chip select assertion, or you don't initialize buffers properly, first few RX bytes can be junk. Page you Send, specify how many bytes you want to transfer. L? Wasn't L a loopback? I'm gonna paste this. S. What was S? Send 32 bytes. Oh, transfer size. Interesting. Okay. I feel like I need to reboot. Things have probably gone out of sync. Device size 32 bytes. Control 13, 14, 15, 16, 17, 18. 32. Okay. I'm not specifying speed. Interesting. Curious what it says about this. I mean, who knows what is on the FPGA currently. That's why I wanted this to finish. Still going through it, huh? Dummy transfer of the same size before your real transfer. This clears the old RX data from the hardware buffers. Interesting. But I mean, I still see that the incorrect first couple bytes, first word, first 32 bits. Messed up. Huh. Interesting. Oh. So instead of this, actually capture and consume the RX output. Let me transfer to clear garbage and see what we got. Now the real transfer. Isn't that what I did? Oh. I think I see what it's saying. Okay. It's almost like you need to run this. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. You ignore what you receive. So this is garbage. But the actual value you care about is on this interaction. No, that still didn't work. Yeah, this doesn't seem to be working. Something weird is happening. Oh, this is taking a while. Right. You can get part of the previous TX bleeding into the next RX, yes. Some transfers start midstream, yes. Not flush just by doing dummy writes, yes. It doesn't fully drain the FIFO after transfer. It's very normal for using a SPI controller when used with raw. Use raw without a tight driver that manages chip select and FIFO drain properly. Interesting, okay. Interesting, okay. So saying SPI Dev 2 is not good enough. Then I may want to go to something like an Arduino then. to test interactions with this. Okay. Well, I think I'll do one last ditch effort and try to get this running. If this CH Owen will ever finish. Might just cancel this and just see if it'll run. See what happens. Alright, I'm just gonna cancel. Okay. What was the next step? I think it was source build. Run the Yocto image. That should be running this at the bottom here. So it's going to be running the RoboDog image. Hopefully this will work. Again, it's been a while since I ran this, so. Looks like stuff was cached, hopefully. Definitely don't want to wait here for like an hour or two. Yeah, okay. Yeah, stuff was definitely cached. You can tell because it jumped straight to recipe 5500. So right now I'm just creating an operating system, or like creating, yeah, I guess it would be creating an operating system. It's using a lot of what I used in cache a long time ago to create it, except it's just replacing the parts that I replaced with the bitstream when I built this. So building that FPGA project gave me a Xilinx shell archive, or XSA, like a bitstream. And then had like other stuff like a first stage bootloader in it. And we packaged it in HDF right here. This is where temp spy 1 was. You can see first stage bootloader being configured, and it's going to be built. V4L. It's video for Linux. Some of these, it just might be like, it's been so long since I pulled this. I would have expected it to just like build U-boot and some of the like maybe core Linux stuff. This. But it might be pulling upstream stuff, and some stuff might have changed in the branch that I'm on. That's a bummer though. That, I mean, if this is really the case and I'm still having this issue. Yeah, if I'm still having this issue on this new build that I'm building right now, yeah, I'm gonna have to probably switch to an Arduino. Again, like I don't necessarily need the Zybo board for anything, for testing this. It was just nice because I knew it could do SPI, but I guess it's having issues, so I probably won't get to doing the Arduino in this stream. Probably do it in the next one if that's what I have to resort to. I mean, I don't care what device it is, I just want any SPI so I can access this. I could probably put the headers on right now while this is going. Yeah, why don't we do that? So I'm gonna switch over. Let's see, I'll point you guys down so you see what I'm doing. Oh. Okay, let's see, what do we need? Let's get header for this. What is it? 1, 2, 3, 4, 5, 6, 7, 8 pin. I might have an 8 pin in here. Let's see, pin 1, 2, 3, 4, 5, 6, 7. Just need one longer than this. 1, 2, 3, 4, 5, 6, 7, 8. Let's use this. Yep. So I'm going to solder them on just like that. Right, this fits into that pitch, right? Yeah. Okay. Just thinking if I have something to hold. I mean, honestly, I might be able to just get away with putting it like this, soldering it on the top. Might actually just do that. You guys see that? Sort of. Oh. Not enough. Well, it's not the best, but it should work. All right, well, looks like that's good. So this will probably be ready for next weekend when I stream and get a different method if the Zybo board isn't going to work for the last whatever many minutes. Last 30 minutes I do this. I'm not going to stream for too much longer, but I do want to see if this new build finishes and if this works. Yeah, seems good. So it looks like there's a little bit more to go. 99% for the whole build, 50% on the OpenCV compiling. I guess I could I'm kind of tempted to plug in Mosi and Miso from that chip into the Zybo board just to see what I get out, but I mean, if I can't trust a loopback, I don't think I'd be able to trust the data that's coming out of the chip, which is unfortunate. There was a SpyDev test loopback on this. Yeah, I don't know what that means. D-message. Does this give me any information? Oh, this is my driver that I was using. Supported mode bits 20. Mode bits per word. Does that need to be something? 32 bits per word? What if I remove? Oh. 16? 8? Oh. Interesting. What if I do this? E8. Yeah, still offset. What if I do -L? Yeah, it's still messed up. All right, well, we just have to wait for this new image to build. So let's wait for that. It's almost done. So once this builds, I'll get a SD card, or I'll get an image for an SD card. Actually, I can probably start preparing that now. I'll use a new SD card because I don't want to mess up the one that I have now, because on the last stream I did image processing and I made sure that that works. So let's just do this on the new SD card. So I have a new one right here. So I'll get a USB SD card reader. So something like this. And I'm going to put this in my computer. Oh, I can put it here actually. I'm just looking to see what I was doing to flash some of the components onto the SD card, like in what region I was like looking at. Man, it's been a while. So I'm using WSL2, so I have to do these weird things to like mount an SD card into the WSL2 environment. Okay, I'll just run this as is. So like there's a connect. Is connected, and I see SD card here, but I actually want to unmount that. So you mount. You unmount unmount an SD card, probably disconnect. You mount. Okay. Let's go back. SD card, you mount. And then sudo u mount. So that means if I go into mount one, I do df here. No, it is mounted. How can I not u-mount? mount one not mounted, but it was, right? So can I just remove it? Oh. Okay. So that means I mounted, so dev SDD, right, so that still exists. Dev SDD, yeah. Okay, so it's making the image now, rootfs. I'll go to the image. RoboDog, workspace, hockey, build, temp, image, deploy image, sync generic. That's in here. So I think there's multiple ways to like flash an image to an SD card. Like you can take the root file system and then flash that on specific partitions. What you saw was like a mount in one of those partitions that I was going to flash in, but I have a better way to do it. If there's like a .wic file, it creates the partitions for you. So hopefully by the end of this, it'll create a .wic. I don't see one here from the previous build, but I might have deleted it because it knew it was building a new one. If it doesn't, we have to do it the old-fashioned way, which is mount, create 2 new partitions. I'd rather not do that if I don't have to. Mess around with this while I'm waiting for this. Yeah, as you can see, there's like a FIFO buffer that's not being flushed. I have a feeling like even if we go to this new operating system, I'd still run into this issue. There it is, it's getting the wick. DD command for flashing wick to SD card. DD is disk dump. Including removing any files. In Linux. Okay. cool. Finished. Ran everything. I'll zoom in here. I think I was in SDB, right? SDD. Okay. SDD. Not mounted, not mounted. Okay. Yeah. So I just need to do this to SDD. I need to make sure to change that, otherwise I'm going to wipe out my drive. Okay, so the wick should be in here somewhere. Where? Wick. Should be another wick. I'm missing it. Dot wick. That can't be done. Is this the only way he creates? Really? I'm not just missing it, right? No, those are the only two wicks. Interesting. QEMU is like an emulator. I would not have expected this to end in QEMU, but I should still be able to use that for like an SD card for an actual image, hopefully. I'm gonna flash it, so. So is SDD the image that I want to flash? It's right here. Actually, before I run this, where is this pointing to? Because I think that's a symbolic link, right? Yeah, it's just pointing to this. It's the root file system. I'm hoping that's more than just the root file system though, because it should have the boot files in there. Well, we'll see what happens with this, because if I flash a wick, it should contain two partitions, one for the booting, it's like U-boot and Linux kernel and stuff, and then one for the root file system. So I'll see pretty quickly what it's doing after it flashes. Sudo input file, this output file dev std. I know my face is blocking this. Status, progress, okay. That seems right. Just to confirm one last time, this is SDD that it was trying to mount above. Right. Yeah, SDD, okay. You know, this looks like it's paused. I think it's still going. I think I've had issues in the past where like the status wasn't like showing progress when it really was. So I'm gonna let this run a little bit longer. Yep, there it goes. Okay. So supposedly the wick is finished. What I'm going to do, just to confirm what I'm getting out of this thing, so I'll go to my scripts. I'm going to disconnect from it. My SCSI. Program was here. I'm going to stop this, close out of it completely, and then I'm going to go back into it. Reconnect. Yeah, okay, so there's two partitions, and that's exactly what I would have hoped to see. And I can go to those partitions, and this should be, yeah, uboot, zimage, uimage, it's Linux kernel stuff, uboot.bin, that's uboot, the bootloader, this all looks good. And then the mount 2 is all root file system stuff. We'd expect to see on like a Linux distro typically. So that looks good. I'm going to go to disconnect. Yep. Okay, looks good. Start this and close out. Okay. I'm going to, oh yeah, SD card is here. I'm going to put this in the Hoverboard and see what happens. I could technically just like see real quick. Oh wait, which one's body? Or sorry, which one's I think it's comp 5. So this is its serial port. You'd be able to see it log in, or like startup at least. Okay. So I'm gonna turn it off. Here. I'll give you guys a view of what I'm doing. So turn off the Zybo. Actually find where the SD card is. Where is that SD card? Somewhere. Okay. Is this it? Yeah, that's it. Okay. Boy, I hope I'm gonna be able to get this. Oh. Okay, there we go. I'll save this. Let's turn this on. Okay. Start session. Oh. Question is, will it turn on? and turn it back on again. Oh, there we go. Is it getting stuck? No way. It's just getting stuck in the boot sequence? That's interesting. Waiting for root device. I wonder, oh, even the WIC looked right. Like when I was looking at the file system, it didn't know us in it. Maybe there might have been something else that I didn't know that needs to be in there. Let me try one more time. Stopped in the same exact place, huh? Why wouldn't it be able to find it? If I use, just see if I use the other SD card. Should be able to find it immediately on the other SD card, right? And this is the original SD card that I had in there. Just a sanity check. Okay. Let's see. Start. Yeah, definitely past that point. So I'm curious if that's because I'm using the QEMU SD card, or the QEMU WIC right here. But I don't see why that would have done anything different. I can try connecting this again. Whoops, I need to do that. Go away, go away, go away. Okay, let's try connecting to the SD card again. I'm going to connect to the SD card and manually write the root file system to it. Oh, did I? Oops, I didn't have this up. So run as administrator.
Start, connect. Okay. Card, two. So I'm actually gonna remove everything in here. And then the location that I actually need to go to for this is in here. This is where the original WIC was. The root file system actually lives here. This is the root file system. So I was using this. Where's the WIC that I was using? I was using this WIC, but maybe it's because it's only for QEMU, which is like an emulator. I thought I could get away with using that flashing, but maybe not. So I might have to flash both of them. Let me see what scripts I have. iSCSI, remote, rootfs flash. So what did this do again? I think this scripts RoboDog project. Home directory, SD card, mount 2. Yep, I think this does what I want it to do. So I'll do this. So putting root file system on mount 2. It's taking a while to load something on there. Okay, and now let's run boot flash. See if that clears first. Yeah, I do clear out that directory first, which is good. I want to flash. Okay, cool. Let's see what this does. So now I'm going to disconnect. Close out of this. Okay, let's try this again. Turn off the board. In hindsight, I should have probably mounted this board with the SD card in front. Okay. Turn it on.
Let me turn back on. Feels like it got further, but did it not? Oh, you guys can't see what I'm looking at. Sorry. Let's look at, there you go. I want to try turning it off and turning it back on again. Oh, what a bummer. So I'm gonna have to figure out why. Oh. You know what? I might know what it is. Oh, okay. Because this is a custom driver that I created and it's interfacing with something that I put on the FPGA, it's trying to interface with it. And when I load in the driver, it's probably crashing because that thing that I'm trying to interface with into the FPGA doesn't exist. Because I just put a new bit stream on there. Because I mean, you saw what I put on here, right? This is like basically nothing. Like I put a blank bit stream on there, and the only thing that I'm doing is messing around with the mux for the SPI, what pins output to. And this driver is trying to interface with something that doesn't exist. So what I'd have to do, I didn't mean to prolong this stream. I do want to try this though. I would have to remove this driver, which would be, no, in recipes kernel, no. It would be core images, RoboDog image, and where, oh, it's right here. This is all I need to do to remove the driver from the root file system. So I'll just add this here. And I would just need to do, there is sh. That's the command. Take RoboDog image. This should be much quicker because I'm removing something. And it should have cached what I previously did in the last run. So I'll have to flash something new again. You know, this is kind of good. Like I did want to see if SPI would work through this because I wanted to see if this would be like a appropriate pathway for this sensor that I'm working with, the absolute encoder. Like I wanted to see if it can go through the processor, like through the operating system. Like I just wanted to see how that interaction would work. Obviously there's like some hiccups with the FIFO buffer being lagged, and
Just wanted to go with the simple build here to see if that would fix it, but might be more trouble than what it's worth. We get the SD card out of the Hoverboard. Okay, we'll connect this again. Okay, and then let's wait for this to finish. EMS absolute encoder. While we're just waiting here, I'm going to show you the principle and how this is supposed to work. This is the AMS encoder that I'm working with right now. So the magnet's on here, and then as you turn left and right, it's supposed to pick up the magnetic the magnetism of the magnet, and then create like an absolute position for you. It's a 10-bit resolution, so you're supposed to query it through SPI. That's interesting that it also has a PWM interface. So that's a path that we can also go down with SPI too, it looks like. Yeah. It's a cool sensor.
Yeah, PWM might be interesting too on the Arduino. I don't think the reason why I want to try to get SPI working is because that's the interface that's on ODrive. Okay, looks like it finished. So let's go back here, zoom in a little bit. So SD card should be there. Okay, so let's do boot flash first. Let's do root of sflash. So it's removing everything on root file system first. So if this doesn't end up working, I will have, this wouldn't be all failure because I will have learned how to relearn, I guess, how to take a XSA file from here, the Xilinx shell archive, and then wrap it into my Yocto project that I was doing before. That's good. There's probably some optimization processes that I could do there. It'd be cool if I can take like a Tickle script from a Vivado project and build that out completely, so I don't have to like run the Vivado GUI to do this. Everything would just be kind of self-contained in Yocto, but it's for another day. All right, I'll disconnect. And I will close out of this. And then let's try the SD card one more time. This will be the last attempt. Okay, that looks good. And I think I'm going to get a shell prompt. Awesome. Okay. All right, so now I'm going to try this one more time. I need to connect. This is a dead session. Okay, there it goes. Yep, that's fine. Okay, and let's try. I think I connected. Wow, I tried a lot. I just want to try normal. Yeah, try something like this. But yeah, I wiped out my ramp file that I created. That's fine. Yeah, something like this.
Try this. A little bit longer. Oh, that was on 0, so it should be on 1. Still Fs. I'm gonna try changing the speed. No. Well, that's a bummer. I had better luck on the first one, huh? Okay. All right, well, I think for the next stream then, I'm going to probably break out an Arduino. Yeah, I think I'm gonna break out an Arduino. I haven't broke one of those out in a long, long time. And try to get a SPI interface working. I think that's gonna be my next best bet. I mean, I could probably use an STM32. I have a couple of those. I'm a little bit more familiar with the Arduino interface though. But that'll be my homework. I will try to find a better device to do SPI communication with. Like I said, it's not all bad because I relearned how to do the Vivado thing, do any Vivado projects and get that integrated into Yocto and create an operating system out of that, right? And then put it over into the Zybo board. So that was good. And I definitely have to do that in the future too, for some things. But yeah, I think I'm gonna end it here. Sorry, wish I could have gotten a little bit further, but that's engineering for you. I feel confident that I'll get something working in the next stream though. Yeah, Arduino is typically like less broad, more specific. I can use other people's APIs specifically for SPI, so that should yield better results than this. And I also have more control. The SPI dev script is sort of like you're interfacing with Linux drivers, and that might not be. I probably need more control than this, like ChatGPT was saying prior. So, anyways, I'll try streaming next week, and hopefully we can get some sensor data out of this thing. All right. Thanks for watching, everyone. Bye.